For this problem, it's best to stick with the picture and not write down the knowns because there's so much context in this picture. And you'll see that when we start looking at how to solve it. So we see this diving board with the fulcrum pushing this kind of this left to midpoint up, a bolt holding the left side down, and a diver, which is in this case just a box, standing on the right edge of the diving board. Diving board is 3.9 meters long. The distance between the bolt and the fulcrum is 1.4 meters. What we have is the weight of the diver being 530 newtons. We need to find the force that the bolt is experiencing, which I'm guessing is going to be an upward force from the diving board. So we need to figure out what that force is. And the force that the fulcrum is experiencing, which I'm guessing is a downward force pushing down on the fulcrum. So let's do a few notation, I guess, transformations here. The F2 that's on the picture, I'm just going to say is the F of the fulcrum. That is this force pointing up, the fulcrum pointing up. F1 is the F of the bolt, so the bolt is providing a force pointing down. And W on the picture is just going to be the force of the diver, which is also pointing down. That's going to be 530 newtons. We're also going to look at a convention. Counterclockwise is positive, just like always. This is a static equilibrium problem. So that means that we will make alpha 0, or not we will make it, but the problem is that the board does not rotate. So the rotational acceleration is 0. And therefore, the net torque is also going to be 0. So that is what a static equilibrium problem is. Let's also go ahead and do some bookkeeping. Let's make all quantities or all parameters. Let's make it positive so that we will deal with when we deal with operators, okay? So all quantities in our equations are going to be positive, and we'll just artificially put negatives and positives when talking about how they relate to which way they want to rotate the board, okay? Okay, so last thing is let's go ahead and find the force of the bolt by making the fulcrum the reference point. Now, the reason why you want to do that is because if you make the bolt a reference point, for example, then the bolt will actually not contribute anything to the problem because torque will only be made by the fulcrum and the diver. If the bolt is the reference point, there's no R or there's no lever arm. So there's not going to be any sort of analysis of the force that the bolt's acting on this diving board. That's why we need to make a non-bolt item the reference point. And you'll see in just a second what I mean. So the fulcrum is going to be the reference point. The bolt is pulling down, which means it's providing a positive torque. And the diver is providing a negative torque. So let's go ahead and say there, you got torque of the bolt being positive, and you have the torque of the diver being negative. So I'm putting a negative sign there so that we can say the torque of the diver is positive, but the negative is just brought out right in front in the operator. That's going to equal to 0. And let's see, go ahead and just delineate it with forces and radii. We see that torque is the force acting on something multiplied by how far from a reference point or a center of a central point is. So we have, in this case, the torque of a bolt is just going to be the force that the bolt is acting on, multiplied by the radius the bolt is from that reference point. So you see why it's important is because you need that R there to not be 0 in order for you to be able to analyze the F. Now let's go ahead and subtract the force of the diver multiplied by the radius or the distance the diver is from the fulcrum. Let's go ahead and isolate F bolt since that's what we're solving for. F bolt is equal to F diver times R diver divided by R bolts. Now this is going to get confusing later on, but for now, we have to know what this is in the context of the problem. F diver we know is 530 newtons. R diver is the R from the fulcrum, since the fulcrum is the reference point. That's going to be 3.9 minus 1.4. And R bolt is how far the bolt is from the fulcrum, which is labeled as 1.4 meters. So just remember that R diver in this case is going to be from the fulcrum point to the diver, which is 3.9 minus 1.4. If you plug all this into the calculator, you get a whopping 946.42857 newtons of force that the bolt is applying to the diving board. Getting it into significant figures that were given to us, which looks like it's 3, we're going to get 946 newtons. And that is part 1. For part 2, we're going to make the bolt the reference point, since we are trying to analyze the force of the fulcrum. So therefore, let's go ahead and make the bolt the reference point. The fulcrum is going to provide a positive torque. Diver is going to provide a negative torque. So we're going to say torque of the fulcrum minus the torque of the diver equals 0. Now let's break it down into F's and R's. We're going to have force of the fulcrum times R of the fulcrum minus force of the diver times R of the diver equals 0. Again, let's be careful. In this case, R of the fulcrum is actually the same as R of the bolt because of our change in reference point. R of the fulcrum is the distance between the fulcrum and the reference point, which happens to be where the bolt is. So it's going to be 1.4 meters. Now in this case, R of the diver is going to be the distance the diver is from the new reference point that we have, which is the bolt. So it's now going to be 3.9 meters instead of before it was 3.9 minus 1.4. So now it's 3.9 since it's 3.9 meters away from the reference point of the bolt. Let's go ahead and isolate F fulcrum. And that's going to equal to F diver R diver divided by R fulcrum. Again, R diver is 3.9, R fulcrum is 1.4, and F diver is 530 newtons. Putting that in the calculator, we get a whopping 1,476.47857 newtons, or I think that's a 2. And again, to put it into the number of significant figures that were presented to us, that's going to be 3. We get 1,480 newtons. So the force, and so now the final answer is reference point independent. It doesn't matter what the reference point is. All we know is that in this situation where the fulcrum's holding up the board, the bolt is holding down a side of the board. The bolt is applying 946 newtons, and the fulcrum is applying 1,480 newtons, and the diver is applying 530 newtons, all in these strategic points, regardless of which area we consider the reference point. It doesn't matter in this case anymore. It only mattered when we were analyzing Newton's second law for rotation. We needed that reference point. In the final answer, it's reference point independent.